Namaste dear students, you're already aware that moving charges constitute current and electric current has heating effects. Are there any other effects of electric current? Can an electric current wire behave like a magnet? Sounds unlikely, isn't it? Let's perform an activity to find out more about it. By the end of this session, you'll be able to correlate electricity and magnetism, appreciate the discoveries made by scientists like Ørsted, and draw the magnetic field lines for a bar magnet. Let's perform an activity. Observe this electrical circuit. Current is flowing in this copper wire, and if you see the position of this needle, the needle is pointing towards the geographical north and south. If I place the compass needle near to the copper wire, you will observe change in position of the compass needle. We see that the needle is deflected. What does this mean? It means that the electric current through the copper wire has produced a magnetic effect. Thus, we can say that electricity and magnetism are linked to each other. Then what about the reverse possibility of an electric current of moving magnets? We will soon find that out. This relationship between electricity and magnetism was studied by Hans Christian Ørsted. In 1820, he accidentally discovered that a compass needle got deflected when an electric current was passed through a metallic wire placed nearby. Through this observation, Ørsted showed that electricity and magnetism were a related phenomena. His research later created technologies such as radio, television, and fiber optics. The unit of magnetic field strength is named Ørsted in his honor. We are familiar with the fact that a compass needle gets deflected when brought near a bar magnet. A compass needle, in fact, is a small bar magnet by itself. The ends of the compass needle point approximately towards north and south directions. The end pointing towards north is called the north-seeking or north pole, and the other end that points towards the south is called the south-seeking or the south pole. Through various activities, we have observed that like poles repel while unlike poles of magnets attract each other. Now let's perform a few more activities. The first activity is to see how the magnetic field of a magnet looks like. For this, we have just fixed a white sheet of paper on the drawing board. I have a bar magnet with me. I am going to keep the bar magnet just below this wooden board. I have some iron filings with me. Let's see what happens when I sprinkle iron filings on this white sheet. What does this pattern demonstrate? If you observe, we have got a very unique pattern on this white sheet. The magnet exerts its influence in the region surrounding it. The force thus exerted can make the iron filings arrange in a specific pattern. So the region surrounding a magnet in which the force of the magnet can be detected is said to have a magnetic field, and the lines represent the magnetic field lines. The pattern which I have received, just to get a little more clarity, we'll perform one more activity. So for this activity, just fix a sheet of white paper on a drawing board and place a bar magnet in the center of it. Notice this white dot which represents the north pole of the bar magnet. Now I am going to keep the compass needle at the north pole. Now when I keep the compass needle at the north pole, the south pole of the needle points towards the north pole of the magnet because opposite poles attract. And if you can see, the north pole of the compass is directed away from the north pole of the magnet. I am now going to rest the needle. I will take a pen and mark the point where the north pole of the needle is pointing. Now we are going to move the needle to a new position such that the south pole occupies the position of the previously occupied north pole. In this way, we proceed step by step. I am just following where the needle is taking us. You can see that the needle is getting rotated automatically. I repeat the steps. You can see how the magnetic compass needle has changed its direction slightly. I get one more point. Again, the magnetic compass needle has tilted to give me another point. Repeating, I get a pattern on the sheet of paper, and if I am going to join all the points, I am getting a smooth curve. So this curve represents a field line. Now, if I am going to repeat these steps again and again, we are going to get a pattern of magnetic field lines in this fashion. You can see the magnetic field lines are crowded near the poles. So if I keep on repeating the steps which we just did, we will get a pattern something like this, which you can see on your screen, which you can see on this sheet. You will observe that the magnetic lines are closer or crowded at the poles. Magnetic field is a quantity that has both direction and magnitude. It is taken by convention that the magnetic field lines emerge from the north pole and merge at the south pole. Inside the magnet, the direction of the field lines is from south pole to its north pole. Thus, magnetic field lines are closed curves. The relative strength of the magnetic field is shown by the degree of closeness of the field lines. Remember, no two field lines are found to cross each other ever, because if they did, it would mean that the point of intersection, the compass needle, would point towards two directions, which is not possible. Let's talk about the magnetic field due to a current carrying conductor. If you take a straight copper wire supplied by a voltage of about 6 volts and plug the key in the circuit, if we place the compass needle close to the wire, the direction of deflection of the north pole of the needle is to be observed. If the current flows from north to south, as shown in the figure which you are seeing on your screen, the north pole of the compass needle would move towards the east. Replace the cell connections in the circuit. This would result in the change of the direction of the current through the copper wire. That is, now the current is flowing from the south to the north. You will observe the change in the direction of the deflection of the needle. You will see that the needle moves in the opposite direction now, that is towards the west. It means that the direction of magnetic field produced by the electric current is also reversed. Observe the circuit. Insert a thick wire through the center and normal to the plane of a rectangular board. Take care that the cardboard is fixed properly. We will connect this copper wire vertically between the 2 points in series with a battery. I have used a battery eliminator over here, a plug and a key. Thereafter, we are going to sprinkle some iron filings uniformly on the cardboard. You would find that the iron filings align themselves, showing a pattern of concentric circles around the copper wire. What do these concentric circles represent? They represent the magnetic field lines. How can the direction of magnetic field be found? Just place a compass needle at a point P over the circle. Observe the direction of the needle. The direction of the north pole of the compass would give the direction of the field lines produced by electric current through the straight wire at that point. We can show the direction by an arrow. Does the direction of magnetic field lines get reversed if the direction of current through the straight wire is reversed? What happens to the deflection of compass needle placed at a given point if the strength of current in the copper wire is changed? To see this, you can even vary the current in the wire. We find that the deflection in the needle also changes. In fact, if the current is increased, the deflection increases, and when the current is decreased, the deflection decreases. It indicates that magnitude of magnetic field produced at a given point increases as the current through the wire increases. If we place the compass at a farther point from the conducting wire, we will observe that deflection of the needle decreases. Thus, the magnetic field produced by a given current in the conductor decreases as the distance from it increases. It can be noticed that concentric circles representing the magnetic field around a current carrying straight wire become larger and larger as we move away from it. So dear children, what have we learnt till now? A current carrying wire produces a magnetic field around itself. The magnetic lines, the magnetic field lines are in the form of concentric circles, starting from the North Pole, ending at the South Pole. Around a current carrying conductor, the field lines are concentric circles. The magnetic field produced depends on the strength of the current and the direction of the current. As we go further away from a current carrying conductor, the magnitude of the magnetic field produced by it decreases. So I'm sure by the end of this session, you are all geared up to do these experiments with your teachers and with your friends. So till next time, keep practicing. Namaste.